Number 2 is a tricky bit of math for a variety of reasons, not the least of which is that they are interested in the delta H of the reaction, but they are telling you most of the information about what's going on, about the situation going on with the surroundings, not the system. Let me explain. So what you've got here is you've got a beaker of water, or I'm sorry, hydrochloric acid, essentially water, as far as its density and specific heat capacity is concerned, that you've got 75 milliliters of hydrochloric acid that is here, and apparently it's at 18 degrees Celsius. Now what we're going to do is we're going to put in 2 grams of calcium. So once again, we know that delta H is equal to the Q per the mole. So let's go ahead and take care of the moles right away. I was given 2 grams of calcium, and so since calcium weighs 40.1 grams per mole, here that 2 grams is really 0.0499 moles. So I'm just going to go ahead and take care of that and put that in. This is 0.0499 moles down here. Okay? So we're going to go ahead and take 2 grams of calcium and we're going to put it in the hydrochloric acid, and apparently what's going to happen is that it's going to get hot. How do we know that? Because it says it went from 18 to 23. So this thing here got hot. So the reaction that was going on gave off heat so that it went from 18 to 23. Did you catch that? Remember that the Q lost equals the negative Q that is gained, or the Q of my reaction is going to be equal to the negative Q of what's going on in the calorimeter. I am measuring things by the calorimeter, but I'm really interested in what's happening in the reaction. So whatever math I do here for my calorimeter, I'm going to have to take the opposite of that, and that's really what I'm interested in as far as the reaction is concerned. So they tell you in the problem that you've got a density of the solution is 1 and the specific heat capacity is 4.18. So what you've really got here in the calorimeter is you've got MC delta T, because you've essentially got a water situation going on. So the specific heat capacity, they told us, that was 4.18 joules per gram degree Celsius. They told us that it went up by 5 degrees Celsius. Remember, it went from 18 to 23, so we went up by 5 degrees Celsius. Now here's your last little bit. They told you that the density of the solution is 1. There it is. They told you that. And they told you that it was 75 milliliters, right? So what you're going to want to do is you're going to want to come down here and you're going to want to put in 75 grams. Except, don't forget the 2 grams of calcium. The 2 grams of calcium is in the calorimeter as well, so we have to include that because its temperature is changing as well. So instead of 75 grams, you need to make sure that you add 2 to that to get the 77 grams that includes all of the reactants that are going on that's there. So what you got here is you got your 77 times the 4.18 times the 5, and so you end up then with a 1609 joules by multiplying all 3 of those guys together. But remember, that's what's going on in the calorimeter. I'm interested in what's happening with the chemical reaction. And the chemical reaction is going to be the opposite of that. Think about it. How did this thing get hot? It got hot because the reaction gave off energy. And if it gave off energy, it must be what? Exothermic. And if it's exothermic, then you need to have a negative value, which is why that negative is there. So then what you end up with is you end up with negative 1609 joules down here, divided by the 0.0499 moles, And if you turn that into kilojoules and everything, you get about negative 32.2 kilojoules per mole. So that is a tricky, tricky problem here for this guy. You really have to be on your game to get these types of chemical reaction calorimetry problems correct.